Hey everyone! Ever wonder how AI models adapt to new situations without being explicitly told the rules? Imagine teaching a robot to recognize cats in a new environment. Maybe the lighting's different or the angles are weird. That's where unsupervised domain adaptation, UDA, comes in. It's the tech that lets models learn from one dataset, the source, and apply that knowledge to another unlabeled dataset, the target. But here's the catch. The target data is completely unknown during training. No labels, no hints, just pure adaptation. So why is this so hard? Think of it like learning a new language. You've got a textbook, the source data with clear examples, but the real world, the target, is full of slang, accents, and context you didn't study. Traditional methods try to measure how different the source and target are, like comparing the textbook to a random conversation. But here's the problem. Those methods often focus on the worst-case scenarios, the rare, tricky cases that might not even show up often. It's like worrying about a single weird accent when 99% of conversations are normal. Enter this new research. Instead of chasing the worst case, the authors take a fresh approach. They model the uncertainty a learner faces as a probability distribution over all possible true scenarios. Think of it as a map of all the ways the source and target data could differ, along with the best classifier for each. This shifts the focus from rare outliers to the average difficulty across all possibilities. The key innovation: a new metric called Posterior Target Label Uncertainty, PTLU. Here's the idea. When you train a model, you're not just guessing the target labels, you're dealing with uncertainty about what those labels actually are. PTLU quantifies that uncertainty using information theory, like a confidence score for the target domain. If PTLU is high, it means the model is really unsure, like trying to translate a conversation full of idioms. If it's low, the model is more confident. And here's the kicker. The researchers prove that PTLU bounds the model's performance. Higher uncertainty means harder learning, plain and simple. They even introduce an empirical version of PTLU, ePTLU, that can be calculated directly from the data, without needing to know the target distribution exactly. It's like having a thermometer for the difficulty of adaptation. So why does this matter? Traditional methods might say, these domains are really different, but PTLU tells you how much that difference actually hinders learning. The paper shows examples where PTLU outperforms older metrics, offering a more reliable gauge for real-world AI systems. Now let's dive deeper. Traditional UDA approaches often rely on minimizing domain discrepancy, a measure of how different the source and target datasets are. But here's the flaw. They treat all differences equally, even if some are irrelevant. Imagine trying to fix a car by replacing every part that's slightly worn, not just the ones causing problems. It's inefficient and misses the bigger picture. The breakthrough here is framing adaptation as a risk analysis problem. Researchers split risk into two parts: local risk, how accurate the model is on individual examples, and global risk, how well it performs across the entire new dataset. It's like checking both the fine details of a puzzle and the big picture to make sure everything fits. The math gets really interesting when they bring in information theory. Concepts like entropy, a measure of uncertainty, and f-divergences, tools to compare probability distributions, become critical. Entropy, for example, is like the messiness of a system. If you flip a fair coin, entropy is high because you're equally unsure of heads or tails. But if the coin is biased, entropy drops. By analyzing this, researchers can predict how much a model might struggle when faced with new data. The big breakthrough. They proved that their method mathematically guarantees lower risk under certain conditions. It's like building a bridge with blueprints that ensure it won't collapse. No guessing, just solid math. Their secret: focusing not just on guessing labels, but on understanding the structure of the data. Think of it as teaching a model to recognize patterns, not just memorize examples. For instance, they showed that when a model's predictions become deterministic, 100% confident, the risk drops to zero. It's like a student who's so sure of their answer, they never second-guess themselves. But this only works if the new data isn't too different from the original. It's a balance, like expecting a chef to cook a new dish without the right ingredients. Not possible. The implications. This research gives us a roadmap to build AI that's more robust and adaptable. Whether it's self-driving cars navigating new roads or medical tools diagnosing rare diseases, these mathematical guarantees help ensure systems work reliably. So next time you see AI doing something impressive, remember, behind the scenes, math is making it all possible. This work isn't just theoretical, it's a stepping stone towards smarter, more reliable AI. If you want to dive deeper into the equations or see how this applies to real-world tech, hit that subscribe button. Stay curious, and we'll see you next time.